Scientists extract water and oxygen from moon dust using sunlight, lunar settlement breakthrough. Imagine a future where humans can thrive on the moon, utilizing its resources to sustain life. Recent advancements in lunar research have revealed that scientists have successfully extracted water and oxygen from lunar dust using sunlight. But could this innovative method truly be feasible on the moon's surface? A team of researchers from China has proposed that the soil from the moon could be transformed into vital resources like oxygen and methane, essential for lunar inhabitants to breathe and for fueling rockets. This groundbreaking conclusion stems from their discovery of a streamlined, one-step process for achieving this extraction. However, the question of whether this method is economically viable remains a topic of discussion. The Chinese researchers are optimistic about their findings. The most astonishing aspect of our work was the clear success of this integrated approach, stated Lu Wang, a chemist from the Chinese University of Hong Kong. He emphasized that the combined extraction of lunar water and the photothermal conversion of carbon dioxide could significantly improve energy efficiency while reducing the costs and complexities associated with building necessary infrastructure. Transporting supplies from Earth to a future lunar base is projected to be prohibitively expensive. Studies indicate that sending just 1 gallon of water to the moon could cost around $83,000, and each astronaut would require approximately 4 gallons daily. This stark reality underscores the importance of finding alternative sources of water on the moon. Fortunately, the moon is believed to harbor substantial amounts of water, albeit not in an obvious manner. Water has been delivered to the lunar surface through impacts from comets, asteroids, and micrometeoroids, as well as from the solar wind. It is thought to be trapped in permanently shadowed craters at the lunar poles, often found within minerals like ilmenite. While extracting water for consumption is relatively straightforward, with various technologies available, such as heating the lunar regolith using concentrated sunlight, the Chinese team has taken this a step further. They have innovatively utilized lunar soil as a catalyst to break down carbon dioxide molecules and combine them with the extracted water to generate methane. Philip Metzger, a planetary physicist from the University of Central Florida, noted that this approach is novel and could revolutionize how we think about resource utilization on the moon. Methane is considered a more stable and manageable rocket fuel compared to liquid hydrogen, requiring less complex machinery to store and maintain on the lunar surface. When combined with oxygen, liquid methane becomes a powerful propellant. Companies like China's Land Space are already exploring methane-powered rockets, indicating a shift in the aerospace industry. The Chinese team has developed a one-step process to produce oxygen and methane from lunar soil. They first heat the regolith to 392 degrees Fahrenheit, 200 degrees Celsius, using focused sunlight to release water. Then, they introduce carbon dioxide, which could be exhaled by astronauts, allowing the ilmenite to catalyze the reaction between the water and carbon dioxide. This method, known as photothermal catalysis, was tested in a lab using simulants based on lunar regolith samples returned by China's Chang'e 5 mission, as the actual lunar samples are too precious to use in experiments. While previous methods have achieved similar results, they required multiple steps and additional machinery, often relying on catalysts that would need to be transported from Earth. The Chinese team's approach is believed to be more efficient and cost-effective. However, Metzger expresses some skepticism about the practicality of this method. He points out that lunar regolith is an excellent thermal insulator, making it challenging to heat the material thoroughly. The heat does not penetrate deeply into the soil, which significantly limits the amount of water that can be extracted in a given time frame, he explained. One potential solution could involve tumbling the regolith to ensure even heat distribution, but this would complicate the process and slow down water extraction. Moreover, there are concerns regarding the availability of carbon dioxide. Both the Chinese team and Metzger acknowledge that astronauts may not exhale enough carbon dioxide to meet the demands of the process. Metzger estimates that astronauts could only provide about 1/10 of the required carbon dioxide. While transporting carbon dioxide from Earth is an option, it contradicts the goal of utilizing lunar resources to minimize costs. In the long run, however, bringing some materials from Earth might prove beneficial. Metzger cites a similar experiment that utilized a specialized granular catalyst, nickel-on-kieselguhr, rather than lunar regolith. He believes that a purpose-designed catalyst could outperform lunar soil, and although transporting it from Earth would be costly, it could be reused, making it a more efficient long-term solution. Despite the challenges, the research team has convincingly demonstrated that lunar regolith can be used as a catalyst for producing fuel and water. The next step is to determine if this technology can be scaled up to support a sustainable lunar base more effectively than existing methods, all while functioning under the Moon's harsh conditions, including extreme temperature fluctuations and intense radiation. Metzger remarked, "These results are intriguing, and there may be further applications for using lunar soil as a photocatalyst. However, more research is necessary to establish whether this concept can be economically viable." I remain skeptical, but every innovative idea faces its critics, and true validation comes from rigorous testing. As we look to the future, there is no immediate urgency for this technology. With NASA's Artemis 3 mission set to return astronauts to the Moon by 2027 at the earliest, and funding for subsequent Artemis missions still uncertain, we are not yet ready to establish a permanent lunar base. However, the Artemis missions present an excellent opportunity to test these technologies, which could be crucial in determining our ability to live on the Moon. This research was published on July 16 in the journal Joule. Keith Cooper, a freelance science journalist and editor based in the UK, holds a degree in physics and astrophysics from the University of Manchester, and has authored works on extraterrestrial intelligence and various topics in astronomy and space science. Unlocking lunar resources. How lunar regolith can support a moon base. Unbelievable as it may seem, lunar regolith, the dusty surface of the Moon, holds the key to sustaining life on our lunar neighbor. This innovative idea combines light and heat to unlock essential resources from the Moon's soil, offering a sustainable solution for long-term missions. Imagine a world where we don't have to rely on Earth for every little thing. Instead, we can harness the power of the Sun and the Moon's unique environment to create the very elements we need to survive. It's like a cosmic recycling plant, but way cooler and more futuristic. The process is deceptively simple: water, carbon dioxide, and a special catalyst found in the regolith itself. By applying heat and light, we can break down these components and produce hydrogen, oxygen, and carbon monoxide. These elements are the building blocks for rocket fuel, life support systems, and even the creation of other useful hydrocarbons. But here's where it gets controversial: the catalyst, ilmenite, is not as efficient as we'd like. It's a bit like trying to bake a cake with only half the ingredients. It might work, but it's not going to be perfect. And this is the part most people miss. The extreme temperature fluctuations on the Moon could wreak havoc on our chemical processes. Despite these challenges, we have time on our side. It's not like we're rushing to get back to the Moon tomorrow. In fact, it might be years before we set foot there again. So, we can take our time, refine our processes, and create a robust system that can withstand the Moon's harsh environment. So, what do you think? Are we ready to embrace this lunar resource and its potential? Or do you think we should stick to more traditional methods? Let's discuss in the comments and explore the possibilities together. Breakthrough device produces water, oxygen, and fuel from lunar soil. Imagine unlocking a life support kit hidden inside ordinary moon dust: water to drink, oxygen to breathe, even fuel for the trip home. Sounds outrageous. Keep reading. A Chinese-led research group now says a simple, sunlight-powered reactor could make that sci-fi scenario real, and they have lunar soil in hand to prove it. But here's where it gets controversial. Is the method robust enough to keep an entire moon base alive? Or is it just a laboratory curiosity? The study, headed by Lu Wang at the Chinese University of Hong Kong, relied on genuine lunar grains collected by China's Chang'e 5 mission, along with Earth-made imitations for comparison. By exposing these samples to concentrated sunlight and recycled astronaut breath, rich in carbon dioxide, the team showed that moon dust can do triple duty. 1. First, solar heat drives water out of the minerals, a resource long known to be trapped in lunar rocks, but rarely harvested efficiently. 2. Next, the same dusty material acts as a catalyst, helping water and co-react to form carbon monoxide, hydrogen, and extra oxygen, ingredients for rocket propellant and breathable air. 3. Finally, any spare water extracted in Step 1 remains available for drinking or farming. Early evidence points to a mineral called ilmenite as one of the catalytic MVPs, though other compounds may also lend a hand. The chemical pathway is fascinating and could be central to in situ resource utilization on the moon, notes Hai Hui Joy Jiang of the University of Sydney, who was not part of the project. And this is the part most people miss. Scaling up from a benchtop rig to a full-blown lunar factory is no walk in the regolith. Wang readily admits the hurdles: wild temperature swings, near vacuum conditions, relentless solar radiation, low gravity, uneven soil chemistry, and a surprisingly limited supply of coal once a small crew exhales its share. Each factor could cripple efficiency or damage equipment if engineers don't plan carefully. Still, the allure is huge. A self-contained, solar-powered system that turns local dirt and astronaut exhalations into vital supplies would slash launch costs and extend missions far beyond today's limits. Practical? Maybe. Game-changing? Absolutely, says Wang, while also calling for larger prototypes and long-duration tests. The paper, originally published on the 16th of July, 2025, and amended on the 18th of July to clarify that some water survives the hydrogen-oxygen reaction, leaves open several big questions. How large must the